industry experts and academic experts from all over who would be giving different sessions on different parts, different aspects of the microgrid. Today's session will be about island detection in refinery cogeneration. Before we start our talk, just a little bit about the IEEE Palouse. The IEEE Palouse is part of the IEEE organization. We form part of the Region 6, mostly comprised of people, members from the Palouse area. We have been, this is the first time we are doing this webinar series, and there are quite a few more sessions to come. So please stay tuned. Watch our LinkedIn page, our Facebook page, our website for more information. So today we have Daniel Jones, who is a project engineer and area lead in the SCADA and Analytical Services business unit in Power Engineers Boise. He received his bachelor's degree from Southern Illinois University and has been working at Power Engineers since 2006. He specializes in system protection and control, power system analysis, and power quality studies. So without further ado, I'd like to welcome Dan, and for the attendees, just a quick reminder: if you have questions during the session, please feel free to drop in your questions in the Q&A section, and we will take all the questions after the talk. So yeah, I'll have Dan now present.
All right, thank you.
Take it away, Dan.
Thank you for that kind introduction, and I'm glad that you said all those things because that way I don't have to. Let me see if I can get a screen shared here. All right, I'm just going to give that a moment to show up. Can everybody see my screen?
Yes.
Oh, fantastic. Okay, so this evening, I'm going to present on an island detection project that Power Engineers did a year or so back at a petrochemical facility. Does not seem to want to advance. What's going on here? There we go. So in the presentation, we're going to answer two main questions. The first one is, well, why was this project needed? And the second one, which is a little more complicated, is how did we do it? So as I said, this is an oil refinery, and the oil refinery has a steam boiler that creates steam for two purposes. One, they use it in their refining process, and they also use some of that steam to run 3 steam turbines for electrical, to supply part of their electrical needs. Whenever these generators were originally installed, they were intended to run with a connection to the local utility. And as such, anytime that they were ever disconnected from the local utility, the generators could not stay online, even if they did have enough available generation to power part of or all of the refinery load. And so the intent of this whole project is to detect whenever that the refinery becomes separated from the utility, and very quickly change the generator modes such that the generators could stay online and power at least part of the refinery. Here's a picture of the system single line diagram, and I'm hoping everybody can see my mouse. So I'm going to point around with it a little bit. So up here on the right is a 46 kV connection to the local utility, a pair of step-down transformers that goes down to this main power distribution center here. Everything below these two transformers is 4 kV. And as you can see that each one of these power distribution centers has refinery loads connected to them. And then there's a big loop that goes from the main PDC, has a tie line down to the power plant. And that's where the 3 steam turbine generators are. And another line over to a PDC, to another PDC, and then back to the main PDC. What is not shown on here, and I'm really hadn't intended to present on, is that there is actually a load shedding scheme in place at the refinery, and anytime that this connection to the utility is lost, they wind up they intentionally dump a bunch of non critical loads up here at this main PDC. So the goals of this entire project is 2 things. Anytime that the refinery electrically becomes disconnected from the utility, we want to know when that happens and detect it, and then very quickly send a signal over to the turbine generator controls to change their operating control mode such that they can continue to run independently of a connection to the local utility. The reason that we're trying to do this is, I don't know if anyone's ever been in a refinery whenever it loses power, but it's not a pretty scene. These processes inside the refineries have high temperature, high pressure, and whenever you lose power to it, things tend to go haywire, and there's usually a lot of fire and certainly very dangerous conditions. In addition to that, anytime the refinery's not refining sludge into gasoline, they're not making money. So it's the intent is to leverage their existing generation to provide systems reliability. So from a development process standpoint, there was basically 6 steps that we went through. And I'm not going to read these steps off of the slide because we're going to cover each one of them in detail in subsequent slides. So at the outset of the project, the first thing we did was create a functional specification. This document describes in a narrative exactly what the intent of the island detection system was supposed to do, how it operates. It also serves as the roadmap for all of the engineering that came after that. And in addition to the narrative on what it's supposed to do and how it operates, it also includes lists all of the major IEDs involved in the system, all the I/O connected to each IED, potential failure modes of the system, and the desired reaction of the system to those failures, enunciation, and then of course the sequential events recording for for testing and troubleshooting and that sort of thing. So inside of the functional specification, it can really be put together. The purpose of this is to gather circuit breaker statuses from all of the various IEDs in the system and determine through Boolean logic if any one generator is in parallel with the utility or possibly with another generator. And then once that determination is made, signals are sent from the island detection system to the generator control system to change control modes as necessary. So after the functional specification was developed, then the next major task was to actually develop the Boolean logic to make that determination. And as I said, there's various IEDs throughout the system connected to all of the pertinent circuit breakers that we wanted to monitor. Those IEDs would then send that status via IEC 61850 Goose messaging back to the central logic processor. That Boolean logic we actually developed in a couple of different ways. The first way, which is obviously harder, is basically by brute force. We inspected the system and logically, built the Boolean logic by pure inspection of the system. Later on, during the testing phase, we actually come up with another quite clever way of creating that logic, and it was through a Python library called NetworkX, and it uses graph theory. And essentially, what we did is we built a model of the electrical system and all of the pertinent circuit breakers, and we're able to query that model and ask it questions such as, is generator number 1 in parallel with generator number 2? And it would spit out the answer. We relied on that very heavily later on whenever we used that library and that the Python graph theory to vet our logic during testing. And then as a follow-on, after we developed the island detection logic, we created logic diagrams. You'll see in a little bit that although this is not necessarily an overly complicated system to look at, you'll find that the logic diagrams actually became quite complicated. We use those logic diagrams for a couple of purposes. One, a visual representation of the logic. Anybody who has ever looked at Boolean logic in text, it is extraordinarily difficult to understand and just look at it and on. It was also extraordinarily helpful whenever we were developing the actual programming in the various IEDs. And then of course, later on, once we got to the testing and troubleshooting point, it's absolutely crucial for testing purposes. So to give you an idea, this is one of 6 logic diagrams that we developed as part of this project. And you can see it's actually quite complicated. There's an awful lot of stuff going on here. And if we didn't create these logic diagrams, well, first of all, programming the IEDs would have been very difficult. And then later on, trying to troubleshoot or even understand somebody else who wasn't in on the development, those folks trying to understand this system without these logic diagrams would be extraordinarily difficult. It is certainly not my intent to go over this level of the logic. Just kind of wanted to give it as a bit of an example of the level of complication we were looking at. One other thing to note, a total of 17 circuit breakers in this system that we were monitoring. And if you do the calculation, it comes out to be something slightly over 131,000 different logical conclusions that you could get with 17 different binary variables. Of course, there's only a small handful of those logic conclusions that result in really any meaningful value. In other words, is generator number 1 in parallel with the utility or in parallel with another generator, that sort of thing. Concurrent to the logic diagrams or the logic development, we were also developing an IEC 61850 spreadsheet. This is basically a document that describes in detail everything that goes into the Goose messaging, such as Goose message ID, and of course a description, source IED name and address, destination name and address, Goose messaging ID to variable mapping in each IED. In concert with let me back up just a slide. You can see over here on the left-hand side, this is the IEC 61850 part of it, and then those Goose message variables get mapped into, in this case, a cell logic variable inside of the relay. So that's what the fifth bullet point, Goose message ID to variable mapping in each IED actually means. We use this spreadsheet along with the logic diagrams whenever we were actually programming the processor as well as the IEDs themselves. Next step was to actually develop those settings, and of course, the functional specification I said early on, that was the roadmap for all of the engineering that was going to come after that. Then of course the IEC 61850 spreadsheet that details everything about the Goose messaging, and then of course the logic and the logic diagrams. So as I was saying earlier, with the level of complication of this logic, it was absolutely crucial that we performed a bench test on these on the logic controller and its settings. The first step in that process was to create a test plan. The test plan, it detailed such things as the pre-test setup, just exactly how is it, what equipment did we need, how were they going to be connected, IP addresses of various things. It also detailed tests on normal operation. Well, sure, we were going to test how it should normally operate, but then of course we wanted to test all the various failure modes and make sure that the system was operating per the functional specification. And another one, I don't know if anyone's ever been burned on this one, but we specifically wanted to test the performance of the system of a live system during IED settings changes. Like I said, we've been burned on that one in the past, and that was one of the specific tests that we wanted to make sure wasn't going to cause us issues. As I said, this is pretty complex logic, and it's just not one of those things that you could really test by inspection. It was really high risk, and it really necessitated a deep dive into the bench testing in order to vet that logic out. And finally, the overarching paradigm that we were working under is testing the system per the functional specification. The functional specification was really the key to the whole project. It describes how the system should work, not how it was actually implemented. Because if you just test what you implemented, well, sure, it's going to work. But we really wanted to make sure it was doing what we wanted it to rather than what we programmed it to do. So in order to do that, to test these 131,000 different combinations, we created a custom Python script and the Python graphing library model. And as I said earlier, that model, what we could do is we could query it and ask it questions such as, you know, under a certain circuit breaker open and closed combination, and all of those combinations, we would ask, is generator number 1 in parallel with generator number 2? Is your generator number 1 in parallel with generator number 3, etc. And what that did is that it basically produced what I call here the answer key. And so we separated out the logic development from the answer key that we're creating in real time here. Once we have that information, we simulated every possible circuit breaker combination, and via a computer connected to a test set, we published goose messages simulating all of those circuit breaker combinations. Once for each combination, the logic processor would crunch through the logic, and then we would query via the test application the result from the logic processor and then compare it to the answer key. So to give you an idea what that kind of looked like, it was actually a pretty simple system. Over here on the left, and this of course is physically how it was connected. We have the test application running on just a normal laptop. It was connected to obviously an Ethernet switch there, and then of course the test set that could publish the goose messages, which were then received by the logic processor over there on the right-hand side. From a block diagram standpoint, it looked like this. So the test application would communicate to the test set over here on the right, which would publish goose messages representing all of the various combinations sequentially, of course, one at a time. Publish the goose messages to the logic processor. The logic processor would then make a determination of whether any one generator was in parallel with another, etc. And then the test application would poll the logic processor via DNP3 to get the answers, and then compare that to the answer key. So as you can imagine, this automated testing sped up testing greatly. If I did the math on it earlier, if we could test one of these combinations, once per minute, it would still take us something like 40 continuous hours of just testing each and every one of these combinations. Which, as you can imagine, that whole idea would be, well, not only tedious, but just absolutely rife with the possibility of human error. I may actually be running a little fast. So once we bench tested everything, and of course we had to spend a little time troubleshooting our test setup because there's a lot of moving pieces there. We tested all of these, all of the various combinations in the matter of hours rather than days or potentially weeks. That allowed us to have a very high degree of confidence that the system would, or at least the logic that we built, was doing exactly what we intended it to. So whenever we took the logic processor from the bench test scenario to the field, we had extreme confidence that the programming itself was correct. The next step, of course, was to install this into a live system in the field. First thing we did was created a field testing plan. That was going to be the roadmap for all of the stuff that we wanted to cover while in the field. Of course, we did recreate some of the bench tests that we did in the lab, specifically the Ethernet and fiber loop failures, and verified that those failures, or at least the system, responded to those failures in an elegant manner. Beyond that, the vast majority of the time in the field was spent verifying that the IEDs in the field were the breaker statuses were A, wired to the correct IED, that the breaker status from that IED was routed to the correct goose message, and that the goose message was routed to the correct variable inside of the logic processor. And the way we did that is literally one breaker at a time, open breaker number 1, and then followed it all the way from the IED to the goose message to the logic processor, and verified that it indeed was showing up in the right spot in the logic processor. Which with 17 breakers is not that difficult, but of course everything you do in an oil refinery always takes longer than you think it should. So here comes the big test, and I am definitely running a little early. So the good people at the refinery actually allowed us to do live system testing on this, and this is really the big test. We can prove in the lab that our logic works. We can prove in the field that all of the IEDs are sending the correct information from point A to point B. But actually simulating an island condition, and when I say simulating, this was done on an in-service live system. So the generators were online. The refinery electrical system was connected to the utility, and they allowed us to do two live fire tests. The first one was an entire refinery island with 3 generators in service. And there was a bit of a glitch in that particular test because there was some configuration or programming inside of the turbine generator controls that was not set up quite right. But the system did 2 things. It did detect that the refinery was islanded, and did send the correct signals over to the turbine generator controls. After that was fixed, we ran another test where we islanded part of the refinery with 2 generators, and in that particular test came through with flying colors. The generators changed control modes, and that partial refinery island stayed energized with no hiccups in the middle. Yeah, and unfortunately, as I said, I ran way early on it, so we have plenty of time for questions.
Not a problem. Thanks, Dan. We do have that does give us some time for question and answers. Thank you for this was quite an informative and detailed presentation. It's good that it's good to have an insight from how an island detection scheme is implemented from conception to design, bench testing, and all the way to field commissioning and testing in the field, right? And so, that's great to have an insight from someone who's worked all the way through from its conception. So thank you for that. And I think we had quite a few Q&A, a few questions from the attendees. And please do send more questions if you have some. We do have some time. So I'll start with the first question. The first question is, what is the general rating of the microgrid? Is it in megawatts or kilowatts?
General rating, that's actually a really interesting question. I was talking to a colleague earlier about it. So I don't know that there's technically a rating in watts or kilowatts or megawatts. In this case, there was approximately about 9 megawatts of local generation, and I think somewhere in the range of about 20 megawatts of load. I always kind of resort to going back to the EPRI definition of a microgrid, and it really talks about a well-defined electrical system that has both loads and generation within it that can operate in parallel with the utility or also operate as an islanded system. Sure. So maybe there's others on the panel who have a different definition of a microgrid with respect to megawatt or kilowatt size.
Yeah, I think when this person was asking, I think specifically to this system. So yeah.
Yeah. Okay. Well, I inadvertently answered the question then.
Yep.
Yeah, they were just asking about, I think it looked like they were just asking about the relative size of it.
Yeah. Okay.
Oh, okay. Yep. So yeah, so about 9 megawatts of local generation, and in the range of about 20 megawatts of total load.
Okay. I have another question that asks if you used any IEEE standards while designing this scheme.
Let me think about that. Off the top of my head, I can't think of any specific IEEE standards other than those that would deal with the networking itself. I said earlier that we did use IEC 61850 for the goose messaging part. Mm-hmm. But not really anything that I can think of from an IEEE standpoint that really dictated what we were designing here.
Okay. Okay. So how did you? There was another question that talked about how did you go about gathering data for designing this the scheme?
Yeah, great question. We've had a relationship with this refinery for many years prior, and I'll go back to the. Hold on a second here. Let me make this big again. I'll go back to the. I'll go back to the single line diagram, and I can kind of talk about a little bit of the history that we had here. So this PDC, the main PDC, this PDC over here called sub 4 and the sub 3 PDC, Power Engineers we were all deeply involved with the design, installation, testing, relay settings, SCADA implementation, networking, fiber design, all sorts of things with those PDCs. They're relatively modern. When I say relatively, they've all been installed in the last 8 years, I think. Down here at this power plant, this thing's a Jurassic monster. It has been around for 60, 70 years. And so this switchgear down here is quite old, and it did one thing I didn't cover in the presentation is most of the IEDs that were involved with the system were installed relatively recently and specified at that time with IEC 61850 capabilities. Down here at the power plant, we actually upgraded several relays down here in order to get the 61850 capabilities needed for this system. Honestly, those old electromechanical relays needed to be upgraded anyway, so watching them go was, I don't think, made anybody sad. So to answer the question, from a data gathering standpoint, most of the data pertinent to the design, we already had intimate knowledge of, and anything else that required data gathering, we actually went to the field. We went to the refinery and gathered it ourselves.
Okay. Okay. So yeah, there's another question that kind of ties into the previous question and what you answered for it. This person asks about how close were your simulation results to the actual testing?
They were identical.
Very identical. Okay.
Yep.
Okay. So what was the programming language you used in the controller?
So in the controller, it was an SEL 2411, and we were using cell logic programming, which is specific to SEL IEDs.
Okay. Okay. So, so what was the round trip time for the load shedding, and for the generator controls? What was the round trip time, and with respect to the islanding event?
That, you know, I knew somebody was going to ask me this, and unfortunately, I don't have a hard number on it. But looking back through the logs, and I'd have to dig all that information up too, I may be able to find that information. Okay. I was talking to a colleague earlier, and it's a great question because, as I said earlier, this has to happen relatively quickly, because if the island isn't detected quick enough, the generators can drift in frequency. Now they have an upper bound and a lower bound, but depending on how big of a load mismatch there is at the time of island, you may actually be able to go either over speed or you know, over frequency or under frequency pretty quickly. So we needed to detect it pretty fast in order to send the signal over to the generator control systems to change mode in order to essentially catch the rest of the system before the generators tripped off on under frequency or over frequency. But unfortunately, I don't have a good number for you on that. I don't know how fast that it happened in the implementation.
Right, of course. Were there any specific challenges that you faced from the conception all the way to the commissioning? Anything that you can recall and bring up?
Good question. Probably the single biggest challenge was developing the logic itself. Right. The second biggest challenge was testing that logic in an accurate and expedient manner, and that's where the automated testing really shone. Without that, testing this system would have been a nightmare.
Yeah, I know. Yeah. So we have another question. What was the trigger for the load shedding? Was it a utility breaker opening or under frequency threshold or anything else?
Yep, good question. So I was saying that the 17 circuit breakers, I wonder if there's a way I can pull up a, no, that's not what I want. I'm going to see if I can pull up some sort of tool that I can. I don't think I'll be able to. But to answer the question, we were using circuit breaker status only. I believe it was a decision of the refinery themselves that they didn't want to go with a frequency rate of change element in order to detect an island. And so it is absolutely purely based on circuit breaker status. And this, like I said, there were 17 circuit breakers. You can see there's these 5 here, this number 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think I miscounted, but there was a total of 17 circuit breakers that made up the entirety of the logical determination. If that didn't answer the question, feel free to let me know.
Of course. There was another question that came in. What was the mode that the generator was running before the island?
Yep, great question. So typically these generators, whenever they're running in parallel with the utility, they're running in what is called droop mode. And
okay.
Essentially what would happen whenever a generator went islanded, the generator control system would tell one of the generators to go to isochronous mode, and then depending on whether or not they were in parallel with the isochronous generator, then the other two would either stay in droop mode or go to isochronous mode, depending on how the system was islanded.
Okay. So what was the code doing if you lost communication to one of the 27 breakers?
What was the code doing? In that case, I think that if I remember correctly, the fallback, or at least the safe fallback, was to not do anything. Let me go down to the. Hold on a second here. You can see we have some quality bits down here, and obviously with not having all of the appropriate information from all of the circuit breakers, that you could potentially have the system come up with an erroneous state. And so essentially the safe thing to do here is to really do nothing. So if you lose communications to an IED, it wouldn't allow, or the system wouldn't make an island determination under those conditions.
Okay. So these are all the questions I got via the chat function, the Q&A. Since we have some more time, we can have, if the attendees would like to ask questions directly, you may raise your hands, raise your hand on this app, and I can allow you to talk, and you can ask your question directly. I did see one hand raised, and that dropped.
Yeah,
there was one more question actually in the chat.
There was one more question?
Yeah, just now. How was the quantity of required to shed determined post-islanding?
I apologize. Can you read that question again, please?
How was the quantity of required load to shed determined post-islanding?
Yeah, good question. The load shedding scheme that I talked about early on is an existing load shed scheme, and basically what it come down to is anytime there was a certain couple of breakers, let me go back to my presentation, go to the single line diagram, that anytime these two breakers up here opened, I believe that's the two, because I'm a little hazy on the details with that, because that load shedding scheme wasn't part of this project. But I believe anytime that these two breakers came open, it would shed all of the refinery loads up here off of this main PDC. And that was an analysis that was done previously. And so unfortunately, I don't have any inside information as to how many megawatts would get shed under those conditions.
Okay. If anyone has more questions, please feel free to ask in the Q&A, or if you would like to ask something directly, please let us know. Yeah, there was one more. Yeah, we just have a follow-up question. So this person would like to say that all the circuit breakers are not important for island determination, so we disable the system. Do we?
So yeah, I'm looking at the question here. So that's correct. So there are obviously other circuit breakers in the system, but there's only the circuit breakers that are part of the path from any one generator to the utility. We're part of the system, and so there was probably hundreds of circuit breakers in the actual system itself, but we were only monitoring 17 individual breakers that made up the path, or a potential path, from any one generator, either connected to another generator or out to the utility. I hope I answered the question. If not, please let me know.
Keith had something for you on your chat. Just something that would help you with this discussion.
Unfortunately, I don't see it.
So he says that it was an under frequency scheme that would shed sub 1. It is independent of the island detection scheme.
Okay, great. Thank you, Keith.
This is for the load shedding part.
Right.
Dan,
Yes.
I had a question before you finish. Did you do these tests online? I mean, did your customer let you do this when the whole system is live? And if yes, or was it done, checked after an event has happened for real?
Yeah, that's a great question, and it's possible that I might have covered it a little quickly right here. So on the slide is the customer did allow us, and we were so honestly extraordinarily grateful to them to allow us to do live testing on an in-service system. I suppose one of the things I probably should have talked a little bit about, or could have talked a little bit about, is the installation, and most of the testing actually coincided with what is called a turnaround. And the turnaround at the refinery is either an entire refinery shutdown or a partial refinery shutdown, where they actually pull the refining equipment apart and do maintenance on it. And that is a really great time to also work on the electrical system, because if the refinery is not in service, then that is the really the only opportunity to work on the system when it's not energized. So that's when this system was installed, was during a turnaround. Once the refinery came back online, and before they actually really started to bring up all of their refining processes, that's when we were actually able to do 2 actual islanding events. And it's possibly a bad choice of words here on my part, because I say simulated 2 islanding conditions. Well, what actually happened is the system was online, and we manually tripped the circuit breaker that would island the entire refinery. And that's how the test came about on the live system. And then later on, as I say here, we did a partial refinery island with 2 generators in service.
So was there any power exchange at the point of utility?
There would have been a small import coming in from the utility.
Thank you.
At the moment before islanding, there would have been a net import from the utility, and then of course the once islanded, then that import goes to 0.
Thank you.
Thank you for the question.
We have, I think, time for one more question which just came in. So this person asks that you mentioned that the Python test scripts were used to validate the controller logic. What controller or PLC were the test scripts running in, and what protocol was used to communicate between the test equipment and the controller?
Good question. Let me go up to here. So here's a block diagram of the entire test sub. This is how it was physically connected, but from a communication standpoint, this diagram really depicts what's going on. So the test application itself was running on a normal run-of-the-mill Windows-based PC, and so that test application was it wasn't actually in a PLC. It was in a just on a normal laptop computer. This application, there was actually several different protocols going on here simultaneously, all over the same Ethernet network. The test application, or the PC itself, it communicated to the test set over a proprietary protocol specific to the test set itself. And then of course there was the goose messaging between the test set and the logic processor. And then also the test application communicated to the logic processor over DNP3.
Oh, thanks, Dan.
Thank you.
Do we have any more questions?
I saw several people from Power Engineers on, and I'm surprised those guys aren't chiming in with impossible questions for me.
All right. So since we are getting way towards the to our time, I think we can move on to we can let Dan I'm sure Dan has has something scheduled after 6:30 maybe, or did you say you had some time? Would you like to wait for more questions?
I can certainly wait. I have no time constraints.
Okay.
So if there's others out there who do have questions and they've been waiting to ask, but they think it's too late, well, it's not. I certainly have time.
Yeah, and if you have more questions that come in, we'll definitely direct them towards you. So, so in the interest of time,